So I want to talk about today, I want to talk about compilers and ZKVMs. Why is that? Well, as we know, ZKVMs are quite expensive. So the time it takes to compute a normal program on a ZKVM is generally 1,000,000 times slower than the time it takes to just compile to a circuit directly. So the question I was posing was how we can leverage the structure of a program using compilers. And with these transformations, the question comes as well, what determines a ZKVM? If we change the instruction sets, are we still having the ZKVM or not? These are very technical questions, very nuanced, but in a way we are generating a different universal circuit, and we are having a different ZKVM. The same question can be asked for memory checking algorithms. If we change the algorithms, we also change the universal circuit, and therefore we also change the ZKVM. And with backends, it's a bit more nuanced, but at the same time, a backend kind of determines the hermetization. Hermetization determines the circuit. And even though the proving is orthogonal to the circuit itself, if we will see that the categories of ZKVMs are categorized by the backend of use. Like we have GKR ZKVMs, IBC ZKVMs, SNARK ZKVMs. Those are categories of the using the backend as a main determining of a category. So the outline of this talk is going to be, first we're going to give some context about what has been done. We're going to also talk about what can be done, understanding the pain points of where ZKVMs are currently not working so well. And then we are going to give some examples of how different teams and approaches have addressed these different problems that we are also showing. So before we start diving into details, I want to give some background of what is a ZKVM. So what we see here is an emulation of a CPU architecture, meaning that we have an abstraction of a stack, of a memory, of execution unit, as a universal circuit, meaning that we have one single circuit for all programs, meaning that we also have one verifier for all programs, which is very nice. That allows us to compute and prove any program up to a certain bound from a given set of opcodes. So what do we want? And this is not particular to ZKVMs, but in any proving system, we want to maximize prover and verifier performance. We want to be able to prove large programs. We want to be able to prove the right program, meaning that we don't want to have bugs in our compilers. And we want this to be used. So we want adoption as well of these proving systems. And why do we want in particular ZKVMs? Well, writing circuits is hard. It not only takes a lot of expertise from the writers, but also it's very easy to make mistakes. And different circuits require different verifiers. Whereas in a ZKVM, because we have a universal circuit, we only have one verifier, which means that we are removing the preprocessing step that is normally quite costly. And we want to prove large programs. This is not particularly addressed, as we are seeing with ZKVMs, because they make generally the problem worse. But this is something that at least we want to address in some way or another. By the way, this is going to be a qualitative type of talk, so I will mention things like expensive and cheap and all that. I will go very little into details. But if you want to ask me questions afterwards, I'm happy to go through them as well. So ZKVMs, the stages that we can generally recognize, we start with a compilation of a program into a set of instructions. We execute the program, generating the execution trace or the witness. Then we prove it, and here is where the different categories of ZKVMs come. Sometimes we use folding, sometimes we use the GKR protocol, sometimes we use SNARK, as we said. So we're going to focus on that first step. And then optionally, some people do another layer of recursion to compress and also to achieve zero knowledge. So what has been done? I'm going to go through this very briefly because I think in this room we mostly know about ZKVMs. So basically, we describe every submodule of the ZKVM, like the stack, the memory, the execution unit in a constrained system. We apply a SNARK or a STARK to generate a proof. Generally, we use STARKs because they seem to be concretely more efficient, even though complexity-wise are worse. And then we use some sort of recursion to reduce the proof and verification costs. And again, optionally, we can also do another recursion for ZK. So this is a monolithic approach, and as we are going to see, even though it brings some advantages like developer experience, there is no more need to know about cryptography ourselves. There is a lot of tooling that developers can use. There is more room for auditability, because now we only need to address this set of opcodes instead of any circuit that we are compiling to. And we have a universal verifier, meaning that it's only one verifier for all circuits. The disadvantages is quite clear. It's quite impractical for large programs because the overhead that this abstraction brings is very high. And it means it's very high in terms of computational and memory-wise. And in a way, even though it's a minor problem, we can also introduce bugs in the compiler. So it's not as much as compiling directly to circuits, but it still is something that this approach can bring. So a different variant that was brought in 2008, but mostly recently with a lot of work related to folding, this IVC ZKVM. So the idea is that we are not only splitting the prover, but we're also splitting the statement itself. So we chunk the program into different chunks, and we prove each piece separately, and then at each time that we are proving each of these pieces, we are verifying not only that transition, but also all the proofs from Genesis up to that point. And depending on how much work the verifier does, we have different variants of these IVC schemes. If we have a full verified algorithm inside of each of these step transitions, we have full recursion. Accumulation brought some of the delaying of the verifier up to the last step, with particle decider. And then folding, which is currently the most widely used type of IVC ZKVM, allows us to delay all of the verifier work except for the folding, so to prove that the folding is done correctly up to the last stage. And Supernova brought something really interesting, which is that one of the requirements that this scheme brings is, when I say this scheme is IVC in general, that the function that we are proving at each of the steps needs to be equal. And in the case of ZKVMs, they are comprising the whole set of instructions. So that makes the prover linear to the number of instructions, and that makes it not practical. But Supernova brought this non-uniform IVC, which allows us to pay only for the cost of each instruction that we are computing at each of these steps. Okay, so the advantage is that folding is cheap because this is the only work that the verifier is now doing. It addresses the memory limitations that we were seeing in previous approaches, in which there was this huge ZKVM that was impractical for large programs. And now we also have non-uniformity, allowing us to have some practical use case for ZKVMs, because we only pay the price for each of the instructions and not for the whole set of instructions. The disadvantages is that, and this is where we're going to focus on, it becomes almost the beginning of the exploration of what can be done, is that we are still not exploiting the structure of a program. And in these constructions, the opcodes are executed sequentially. So that means that there's some overhead for the prover, and then the prover time is generally worse than naively compiling or directly compiling to a circuit. So what can be done? Well, the first thing that we can notice is that we can leverage code structure. So before proving any program, we are generating generally the execution trace. So meaning that we know at each gate which inputs and outputs have been passed. And we know the patterns of a program. So in this case, if we look at, let's say, how we can abstractly represent a program, we can see different blocks. So depending on what these blocks are, it means that we have different, even ZKVMs. So let's say that we compile each of these blocks directly to a circuit. and this becomes our instruction set. Well, then we go back to the initial problem of compiling to circuits is very tricky. If instead of this becoming our instruction set, they may become some sort of coprocessors or precompiles that we may find in some of these cases, then this is something that is currently used by many teams, and it can allow to make the prover faster for certain programs. It can be just blocks in which they contain still the set of opcodes inside of them. And this is something that, as we're going to see, is used by some of these approaches to generate blocks that separate abstraction from set of opcodes to something else. Some of these proving systems leverage this notion of data parallel circuits. So we want to identify circuits that contain certain identical pattern or substructure that is identical. And then we want to use these proving systems to leverage this uniform structure. And another obvious generalization of IBC is this thing called proof-carrying data, which allows us to do folding, not in a sequential way, but in a tree-like way. And each of the nodes only depend on the leaves, and by proving the root of the tree, we prove the whole computation. So now we are going to see the different examples of different teams of how they have addressed these particular problems. To start with, I've chosen the GKR ZKVM. So I guess that some of you are familiar with the GKR protocol, which is just basically a bunch of sum checks combined that they layer the circuit into different layers, and each of the layers you apply a bunch of sum checks. So Tyler 13, in one of these papers that he wrote, he proves that this GKR protocol is friendly to data parallel circuits. In particular, this is also going to be important. They don't need to commit to intermediate data because they use the sum check protocol, and also because they use the sum check protocol, the prover runs in linear time. And by the way, this paper is written by these guys here. I think it's pioneered by the Scroll Foundation. So the main idea is that they execute the program, so they know which opcodes are used in the program, and then they group these identical opcodes. That is, it varies depending on which program you are computing, and then they generate proofs for each of these groups, and also a proof for the chip that glues all these opcodes together, meaning that it preserves the global state and the sequentiality of these opcodes. And they do it by something they call asymmetric GKR, and we're going to see that it brings certain benefits, but also is quite expensive in some other ways. So the advantages of this approach is that the prover is really fast. Now we no longer have this uniform circuit, but the program adapts, the prover adapts to every program. Now we're going to see how they address it, because they do it in a two-layer way, so that at the end of the day we have a uniform circuit. It can be parallelized, because now we have identified these data parallel circuits, and then we can apply the distributed Virgo, for example, prover, or the GKR algorithm as they show it here. And then they eliminate the overhead of, as we were seeing, for example, in IVC, of opcode selectors, branching, and the universal circuit. So the disadvantages now is that each program is different, meaning that we no longer have a uniform circuit. And then they have this second layer called a uniform verifier, which is some sort of ZKVM. And it's a recursive step to accommodate all the different proofs that come from the non-uniform provers. So this circuit is huge. And the only intuition I can provide now to understand why this may be practical is that to verify one of these proofs is logarithmic to the size of all these proofs. So it may be somehow traceable. And in fact, they show that it is quite practical for most cases. And one of the other disadvantages that this approach has is that GKR, even though it can be parallelized, it works better when the circuits are very big. And the reason is because they don't commit to the intermediate wires. They only commit to the inputs and the outputs. Shallow circuits like opcodes don't work very well with this approach. So for that, they provide some sort of variant to this approach. Again, they compile the program to assembly, and then they identify no longer they group opcodes into identical groups, but they find basic blocks. So basic blocks, what they are chunks of code that they don't have a jump within. So in this case, we have a for loop, and then because B2 is computing many times and is identical, it becomes a data parallel circuit, and then we can use parallelization to improve the performance of the prover. And again, we have the gluing chip circuit at the end. Again, the advantage is that we have a structure-aware prover. We don't have this control overhead at the opcode level, so now we only have some sort of control overhead at the block, so at the beginning and at the end of the block. Repeated blocks can be proven in parallel, and instructions are no longer shallow circuits because these blocks are generally quite big. But again, the disadvantages are the same as we had earlier, that each program is a different circuit, and then we need this uniform verifier circuit as a recursion circuit at the end. This was released yesterday, so second example I wanted to bring is called Jolt. The main idea of Jolt is that we are now compiling to the composable evaluation tables. So what the composable means is that you can take an evaluation table and split it into chunks as well, like smaller subtables. And then you can provide a combining function that glues them together. In this case, for equality, is the product. So if you destructure this big table into many small ones, and then you multiply them, you have the same result. And they also bring this notion, I mean, they don't bring it, but they use it, the multilinear extensions, to remove the commitments. So now these small chunks that we have splitted, we can create a multilinear extension of that chunk, and because the verifier, if they want to compute it, they only need to do some I think it's logarithmic to the size of the chunk only. That's quite tractable. So they don't need to commit to the matrix anymore. And that makes it appealing to, or tractable, this problem of splitting a matrix into multiple chunks. If we want to go briefly to this example, if we have 4 inputs, so x and y, each of them have 2 inputs, we have tables of vector size of 2 to the power of 4, and we can deconstruct it into 2 vectors of 2 to the power of 2. So the reduction of these matrices is exponential, whereas the multiplication is linear. So you can see how destructuring a huge table, in the case that they use maybe 2 to the power of 64 or 2 to the power of 128, it can be easily deconstructed into multiple smaller matrices. They want to, well, they propose this notion of lookup singularity, in which you no longer need to write circles yourself, which is quite appealing. It makes it more auditable and brings less bugs, arguably. And they have also this extensibility property that if you're thinking of adding new chunks to this ZKVM, you just need to append your matrix into the huge matrix, and the construction is going to be still quite efficient. So how can we use compilers in this approach? I guess that the question boils down of how efficient it is to create one of these evaluation tables. So in the example that we used before with a program, if we identify the different blocks, can we add them? Can they become the instruction set of Jolt? And I mean, again, the question comes how efficient it is to create these evaluation tables. But maybe we don't want to do that. Maybe we want to only use some of them to efficiently improve Jolt, because adding instructions to this huge matrix that Jolt basically consists on is very easy. Just append some other instruction evaluation table. And then again, another question for compilers is what is more efficient is it to add small operations with multiple lookups, or is it to add large operations with few lookups? The last one I want to bring, also very interesting, even though it's not a ZKVM, is Mangrove. This is a paper that recently came, I think 2 months ago. The idea is that now we are compiling a program into identical steps, which we call here uniform chunks, which are also data parallel circuits. If you think of IVC, the structure works also with data parallel circuits. They need to be the same F at each of the steps. In particular, Mangrove takes advantage of the PLONK arithmetization, the vanilla PLONK, because this is very close to data parallel circuits. In PLONK, you have gate constraints and you have copy constraints. Gate constraints can be split very easily, very naturally, whereas copy constraints, they are global. So you may, a block that you create, a chunk that you create in this approach may reference to another chunk that is in a different, another wire which is in a different chunk. But they have a way to address it that we are going to see in a moment. And then once they identify these identical steps, they run a tree-based PCD for parallelization. And they have also a very nice technique of decoupling the leaf computation, as you can see in the right diagram, from the control merging computation. So this is how a uniform chunk looks in Mangrove. You can see that each of the chunks receives the vector of wires, the vector of permutations, and the vector of selectors. They have the constraints of the copy constraints and the gate constraints. And they do something very interesting with the global copy constraints, because they need to prove that some invariant there's an invariant in 2 different parts of the circuit. And then they do some grand product, but because they want to do this chunking, they are able to decompose as well, to chunk this grand product into multiple ones. And even though each of these ones will not result into one, which is the computation that we want to get here, the product of them will be 1 at the end. And one thing I want to note here is that they also realize that the most costly part of this approach is constructing the commitment openings of the commitments that we have here. So they have a very interesting way of addressing that, and they call it commit and fold. So just to quickly recap the advantages, they remove the overhead of multiple opcodes, even though now this singular chunk has some overhead because of the selectors and all that. They have a way of removing the merging logic at the leaves. So in this PCD, they can also tweak the arity of the tree. So if they have a huge, big number of leaves, then most of the computation comes at the leaves. And again, they remove the encoding of the commitment opening constraints. So allows them to have an efficient prover over committed values. And yeah, they also address the problem of memory, and they can be run in parallel. Okay, so these are the 3 examples. There are many more. We have Lurk, we have Nexus, we have other projects that I wanted to bring, but there was restriction in time. So I wanted to just quickly recap what does the future look like. It seems clear that we want a compiler to chunk the statement itself. We want to combine the pieces using one of these techniques. It can be IVC, it can be GKR, it can be lasso for lookups. Seems that we want to also experiment with abstractions outside the CPU unit. I didn't talk about Nexus, but Nexus also talks about coprocessors. But we have seen here how blocks can come to the picture, how uniform chunks can also be used instead of instruction sets. And we want to leverage parallelism to achieve monolithic SNARK performance. This is something that Mangrove claims they do, which is very interesting. And for that, we want to identify what are the data parallel circuits, and we want to apply proof-carrying data. And the last one that Jolt pioneers is the use of lookups. So thank you for coming today. I wanted to ask a question if you know of certain other ways that we can use a compiler to improve ZKVMs. I want to point to some of the work I've written. A report has some time now, but still worth checking. An article I wrote recently. At Anoma, we have a resource machine, and we are experimenting with different backends. So if you happen to have a backend that may be interesting for us, or if you are also researching on this area, I'll be very happy to talk to you. Thank you.
Thanks a lot. All right, do we have any questions for Alberto?
Great presentation, Alberto. Just curious, what served as kind of the foundational inspiration for this work?
Well, as I said earlier, we don't have performant ZKVMs, so it takes 1,000,000 times longer than whatever direct compilation to circuits take. So I don't think it limits a lot the use cases that we have currently for ZKVMs. So the work can be done by tweaking and making things more performant in a very concrete sense of proving systems. But then we also have programs that have certain structure. And then at Anoma in particular, we have a compilers team that they can tweak a lot of the parameters. So we can not only rely on the performance of particular proving systems, but help them in some way. So that's why I'm also interested in collaboration.
Any other questions?
Go for it.
All right, this is not going to quite be on the ZK side of things, but just to get a mental picture in my head, this would almost be like a profile-guided optimization pipeline where you run the program, you find out something about it, and then you adapt the prover accordingly.
Yeah, exactly. And then the decision, this intersection between compilers and ZKVMs, once we identify, let's say, data parallel circuits or repetitive codes or like ECDSA, I don't know, whatever that we identify as in the compiler, how we can leverage that from the proving system. So this constant communication between the two.
Yeah, just placing it in my head.
Thank you.
Okay, I guess that wraps it up. Thanks a lot, Alberto.
Thank you.